Okay, so let's take a look at the first open response. We're told that the twice differentiable function w models the volume of water in a reservoir at time t, where w of t is measured in gigaliters and t is measured in days. The table gives values of w prime sampled at various times during the time interval between 0 and 30, and at time 30, the reservoir contains 125 gigaliters of water. So this is a table of values of W prime, right? This is not telling you the amount of water in the reservoir at different times. Rather, it's giving you values of the rate of change, the derivative, at different times. Part A says, use the tangent line approximation to W, not W prime, to W, at time t equals 30 to predict the volume of water W of t in gigaliters in the reservoir at time t equals 32. Well, anytime you need to write down the equation of the tangent line for any function, your first move is to just write down point slope form, which is y minus y1 equals m times x minus x1. And to use point slope form, you need two things. You need the point and you need the slope. Of course, we're trying to do the equation of the tangent line to the function w. So the point on the line is going to be I mean, it's a bit funny because the variable here is t, not x, right? When I use the equation of the tangent line, the variables are x and y, but in this problem, those aren't the right variables. The variable is t, right? That's the input, and the output is w. So anyway, the point that we're looking for is going to be 30. That's the input. And the output, of course, is the value of w at 30, right? I mean, that's how you always find the y-coordinate of your point for your tangent line, is you plug that input into your function. Well, we're trying to do the tangent line for w, so you're going to plug 30 into your function w. We don't have a formula for w, but they just straight up tell you that at time t equals 30, the reservoir contains 125 gigaliters of water. That means that W of 30 is 125. So that's the point on our line. Now what's the slope? Well, the slope is just your derivative evaluated at 30. So W prime of 30, which you can find from the table, is 0.5. So plugging all that in, we have, well, I guess so I have y minus y1, which is 125, equals m, which is 0.5, times x minus x1, which is 30. And that would be the equation of the tangent line, but I would say that, again, the letters are kind of wrong here. Like, if you solve this for y, then, well, do I need to solve this for y? No, not really. I'm just trying to approximate the amount of water at time 32. So I'm going to replace x with 32. Again, maybe I should be calling the variable t, but whatever. So y minus 125 equals 0.5 times 32 minus 30, and now it's just arithmetic. So y minus 125 equals 0.5 times 2. That's y minus 125 equals 1. So I think y is equal to 126. Cool. Part B, use a left Riemann sum with the three subintervals indicated by the table to approximate the integral from 0 to 30 of w prime of t. And then it tells me to do other stuff. I'll do that later. Let me start by doing that Riemann sum approximation. So the entire interval goes from 0 to 30. The first subinterval goes from 0 to 10. So if I think about that rectangle, the width of the first rectangle is going to be 10. And how tall is it? Well, since I'm using the left Riemann sum, that means the value is going to be determined, the height is going to be determined by the value of the function at the left endpoint of the interval. In other words, the value at 0, so that would be 0.6 plus, okay, next subinterval, it goes from 10 to 22, so the width is 12, and the height is going to be value at the left endpoint, that's 0.7, plus last subinterval, 22 to 30, that has a width of 8, so 8 times value at the left endpoint, that's 1. So let me make sure I've done that right. 10 times 0.6, 12 times 0.7, 8 times 1. Yeah, I think that's right. So that's 6 plus 7 times 12 is 84, so 8.4 plus 8. So that's 14 plus 8.4, so I think 22.4, I think, probably, right? Yeah. 14.4, yeah, I think that's right. Cool, so that is the approximation of this integral, and then it says, use this approximation to estimate the volume of water in the reservoir at time t equals 0. That's like a later value, earlier value net change thing, because you can say that the later value, which is w at 30, is going to be equal to the earlier value, w of 0, plus the integral of the derivative, the net change. So that's this guy right here. Well, we know what w of 30 is. They tell you that at the beginning of the problem. It's 125. And that's going to be equal to w of 0, which is what we're looking for, plus this integral, which is what we just estimated, right? So that's 22.4. And then we can solve for w of 0. So 125 minus 22 would be 103, and then minus another 0.4 would be 102.6, I think? Probably? Yeah. Cool. So that's what I would say. That the units there are gigaliters. Part C, explain why there must be at least one time t other than t equals 10, such that w prime of t is equal to 0.7 gigaliters per day. This is probably either intermediate value theorem or mean value theorem. Let's think about which one it is. Why is it that w prime of t should be equal to 0.7 other than t equals 10? Well, what I notice is that on this interval here from 22 to 30, w prime starts off having a value of 1 and then ends at a value of 0.5. As long as w prime is a continuous function, the intermediate value theorem guarantees that it will take on all values between 1 and 0.5 at some moment between 22 and 30. So in particular, it's going to be equal to 0.7 at some moment between 22 and 30, which is necessarily a different time than t equals 10, right? So the question then, I suppose, is how do you know that w prime is continuous? Pretty tricky, actually. You would get a lot of partial credit on the AP just by saying, like, intermediate value theorem or something. But I think for full credit, you'd have to say the following. What do you know about w? They tell you it's twice differentiable. Well, that means that you can take the derivative twice, okay? That means in particular that, so since w is twice differentiable, w prime is differentiable, because you can take the derivative twice, right? So w prime is differentiable. But you might remember that if a function is differentiable, then it is continuous. Differentiability implies continuity. So this allows us to say that, therefore, w prime is continuous, and that allows us to use the intermediate value theorem. Thus, the intermediate value theorem says there's a moment, well, it says since w of 22 is greater, w prime of 22, since w prime of 22 is greater than 0.7, is greater than w prime of 30. In other words, because 0.7 is an intermediate value between those two values of w prime, there's a moment between 22 and 30 at which w prime is equal to 0.7. Okay, so that's C. Part D, the equation blah 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 gives the relationship between the area A in square kilometers of the surface of the reservoir and the volume of water WT in gigaliters in the reservoir. Find the instantaneous rate of change of A in square kilometers per day with respect to blah blah blah. I was like not paying attention when I was reading that out loud. I was thinking about something else. What does it say? Find the instantaneous rate of change of A in square kilometers. This is just asking for a certain kind of derivative, but you've got to be careful about like what kind of derivative it's asking for. It's asking for dA dt, right? It's asking for the rate of change of A like with respect to time, right? If that's not obvious, one way you could see that, look at the units, square kilometers per day. Do you see what I mean? And the reason I emphasize that is I think it's very easy to look at this equation and just be like, well, A is the function, W is the variable, I'm just taking the derivative of this, and that would give me 0.3 times 2/3, like the 2/3 comes down, W to the negative 1/3. But that's not really the whole story. That would be the derivative if W was a variable. Like, if they asked you for dA dW, like treating W as the variable, that's what you would say. But they're looking for dA dt, okay? W, therefore, is not a variable, rather it's a function. Okay, it's a function of t, which means when we take the derivative of this guy with respect to t, we have to use the chain rule. So with that in mind, the outside function is 0.3 blank to the 2/3. So chain rule says take the derivative of the outside function, which is like, 0.3 times 2/3 blank to the negative 1/3. What goes on the inside? What goes on inside the blank? Well, just W, the original inside function. That's what we had before, but you also have to multiply by the derivative of the inside function, which is W prime of t, okay? So you pick up an extra factor of W prime of t. And we want to know what this is specifically at t equals 30. That just means you need to evaluate everything at t equals 30. So the 0.3 times 2/3, what is that? I mean, I think that's just 0.2, right? 2/3 of 0.3 is going to be 0.2. If you evaluate the W at t equals 30, what's W of 30? Well, again, that's what they tell you at the beginning of the problem, right? It's 125. So it's 0.2 times 125 to the power of negative 1/3. And then W prime evaluated at 30 is 0.5. So times 0.5. So let's see. 0.2 times 0.5 is 0.1. And then times 1 over 125 to the positive 1/3. That's like 0.1 times 1 over the cube root of 125. The cube root of 125 is just 5. So what is that? If you ever have to multiply a decimal by a fraction, just convert them both to fractions. Like 0.1 is 1/10. So that's 1/50th. In kilometers, square kilometers per day. Okay, cool. So that is question 3. Question 4. A squirrel. A squirrel starts at building A at time t equals 0 and travels along a straight wire connected to building B. For t between 0 and 18, the squirrel's velocity is modeled by the piecewise linear function defined by the graph above. At what times in the interval between 0 and 18, if any, does the squirrel change direction? So this is a graph of the squirrel's velocity. So changing direction just means that the velocity function changes sign, like between positive and negative. So it looks like it changes sign at 9 and 15. So at t equals, I'd say t equals 9 and t equals 15 because velocity changes sign at those times. I think that's it. Part B, at what time in the interval 0 to 18 is the squirrel farthest from building A? And how far from the building A is the squirrel at this time? Pretty interesting. Well, if you're given a velocity function and you're asked questions about how far, how much distance, that sort of thing, you want to be thinking about an area under the curve, right? If you integrate this function, you're going to get displacement. Integral velocity is displacement. So, for example, this big area here under the curve between 0 and 9, whatever that area is, that's the displacement of the squirrel from time 0 to time 9. It's a big positive number, which means that from 0 to 9, the squirrel moves quite a lot to the right, whatever the area is here. Then there's this region below the x-axis. Because it's below the x-axis, the integral would be negative. That means that if you integrated from here to here, you'd get a negative number. In other words, the displacement is negative. In other words, the squirrel during this time moves to the left. How much to the left? Well, whatever the area of this region is here. And then finally, this point here, this region here, would be another positive area. So basically, the squirrel moves a whole bunch to the left, the squirrel moves a whole bunch to the right. Okay, this big area here. Then it moves like somewhat to the left, a little bit to the left, and then it moves somewhat to the right, a little bit to the right. So when is the squirrel furthest from the building A? I would say right here. Right here. Because it moves a whole lot, like away from the building. You know what I mean? Like a whole lot away from the building, and then it sort of comes back, so it's getting closer to the building. And then, yeah, it moves away from the building again at the end, but like it's not compensating for the distance that was lost during this time. You know what I mean? Like you're better off just stopping here if you're trying to get as far away from the building as you possibly can. So this time right here, t equals 9, is when the squirrel is furthest away. So furthest away at t equals 9. And how far away? That would be the area of this region. So how do you find the area of this region? I would just break it up into like a triangle and then a rectangle and then another triangle. I think the two triangles have the same area, it looks like to me. So the first triangle, 1/2 base times height, that's 1/2 times the base, which is 2, times the height, which is 20. So that's that first triangle. Then we've got this rectangle. I think the width is 5 and the height is 20. So 5 times 20, that's the area of the rectangle. And then we have another identical rectangle. So just another 1/2, 2 times 20. So what does that give me? This guy and this guy put together would just give me one copy of 2 times 20. In other words, 40. And then this middle term here is 100, so I think 140 feet. It's in feet, right? What are the units? What are the units? Doesn't say. This can't be a real AP question. Like, they would give you units. Right? Am I crazy? Where are the units? I don't know. Whatever. Part C. Find the total distance the squirrel travels during the interval blah blah blah. Yeah, that's just all three of these regions put together, except this region right here. All three of these areas put together, I should say. Except this area here, you want to make it positive, right? For distance traveled, you want to make all of them positive. I think I'll skip that, honestly. Like, you can figure that out on your own, right? Just find the area of these three guys, make this one, positive, add them up. That's going to be the distance traveled. Pretty easy. Part D, write expressions for the squirrel's acceleration, velocity, and distance x of t from building A that are valid for the time interval where t is between 7 and 10. Yeah, some of that's kind of tricky, actually. So the acceleration is probably the easiest because the acceleration, this is a graph of the velocity, right? Acceleration is the derivative of the velocity, and between 7 and 10 the velocity is just this straight line. The derivative is just the slope, and the slope is constant. So between 7 and 10 the acceleration is just the slope of this line, which is a constant, right? Looks like it's over 3 down 30, so I think the slope is negative 30 over 3, so just negative 10. So that's the acceleration function. It's constant, at least on this interval, right? It's just constantly negative 10, constant function. V of t, the formula for V of t is just going to be the equation of this line. You know what I mean? I would start by just using point slope form probably, because we know the slope already, and we know a point on that line. So like point slope form, that's y minus y1 equals m times x minus x1. So let's use this point here, 7 comma 20. So that'd be y minus 20 equals the slope, which we already said is negative 10, times x minus x1, which is 7. Of course, you want a formula for the function y, so you should solve that for y. So you have y is equal to negative 10 times x minus 7 plus 20. And the only thing is the name of the function here that I'm trying to find a formula for is not really y, it's v of t. You know what I mean? It's v, the velocity. And the variable here is not really x, it's t. So it's okay to use x's and y's in this intermediate calculation, but for my final answer I should write v of t equals negative 10 times t minus 7 plus 20. And you can just leave your answer like that. You don't have to expand it or whatever. Position x of t, that is going to be more annoying. You're going to have to you're going to need some kind of integral, basically. So yeah, there's a couple ways of doing it. One way that you could do it is you could say, well, I've already got my formula for the velocity, and the position is just going to be an antiderivative of that. So I just need to take the antiderivative of that. That's true, but there's one little complication that I'll talk about. So let's just start by finding the antiderivative of this function. Actually, I think to find the antiderivative, I would prefer to distribute the negative 10 and collect terms. I think I'd rather do it that way, probably. So if I do that, the function would become negative 10t, what would it be? Negative 10 times negative 7, that's plus 70. But then we've got this plus 20, so I think it's plus 90. I think that's the velocity function. So that would be negative 5t squared plus 90t plus an unknown constant c. And that guy right there is kind of the complicating detail that's a little bit tricky. How do you find c? Well, you need, really, all you need is the value of the position function at some specific moment, and you're good to go, right? If you know the position at a certain time, you're all set. So what do we know? Well, it's very sneaky, but I think we actually know that x of 0 is 0. I think we know the position at time 0 is 0. Because they say at the very beginning of the problem that the squirrel starts at building A at time 0, okay? And x of t represents the distance from building A. Okay, well, if you're starting at building A, that means at time 0, your distance from building A is 0. Do you see what I'm saying there? Well, you can't respond. This is a video. But yeah, hopefully that's clear. So x of 0 is 0, and you can use that to find the value of c. So I think that's actually going to tell you that c is actually just 0. So c is 0, which means that x of t is just negative 5t squared plus 9dt. Cool. Moving on. Oh, this looks like an integral as net change problem if I've ever seen one. Okay. This is question 5. The function g is defined and differentiable on the closed interval negative 7 to 5 and satisfies g of 0 as 5. The graph of y equals g prime, the derivative of g, consists of a semicircle and 3 line segments as shown. Part A, find g of 3 and g of negative 2. Yeah, this is just like later value, earlier value, net change, that sort of thing, right? So I can say g of 3 equals g of 0 plus the integral from 0 to 3, g prime of x dx. Cool. G of 3 is what I want to know. I already know g of 0 is 5. And then this guy here is the area under the curve between 0 and 3. What is that? Well, first there's this quarter of a circle. The radius of this circle is 2. So the whole circle would have area pi r squared. So that would be pi times 2 squared. But of course, that's just a quarter of the circle, so I divide by 4. And then I've got the this part of the triangle between 2 and 3. So 1/2 base times height. 1/2, the base is 1, and the height is 3. So whatever this is. Okay, I don't really care to simplify this. By the way, haven't really mentioned this to you guys, but when you take the AP, you do not need to simplify any expressions. Numerical expressions can just be left like that. Yeah, so you can just leave it. So I'm going to leave it because I don't feel like doing it. And it's not really hard anyway. G of negative 2, it's exactly the same thing. Exactly the same thing. Except now the later value is 0, right? 0 comes after 2. So I'd say g of 0 equals g of negative 2 plus the integral from negative 2 to, I keep screwing this up, int negative 2 to 0. Yeah, that's what I want. Integral from negative 2 to 0, g prime of x dx. G of 0 we know is 5. G of negative 2 is what we want. And then this guy here is just some area under the curve. What is that? So negative 2 to 0, that's just, again, that's just the quarter circle that we found in the previous problem. That's just this guy right here. Just do a little copy paste. Look at that. Okay, so I guess g of 2 is therefore just 5 minus that guy. Cool, all done. Moving on, part B. Find the x-coordinate of each point of inflection of the graph of G. Cool. Well, let's review concavity. Concave, so what does it mean? So an inflection point is a place where the concavity changes. We're looking for an inflection point of G, so therefore we're looking for like when the concavity of G changes. So let's just think about what that could mean. So G concave up means, well, there's 3 ways to interpret it, right? It means the graph of G is happy. We don't have a graph of G, so that's not very useful. Alternatively, it means G prime is increasing. That sounds pretty nice because we have a graph of G prime. Seems like it would be pretty easy to use that level of analysis. Of course, it also means that G double prime is positive, but I don't know. I think this is the right level of analysis. You know what I mean? So an inflection point of G is a place where G prime, this graph right here, switches between increasing and decreasing. So when does that happen? At 0, right? And then again at 2, and then again at 3. I think that's it, right? switches between increasing and decreasing. Yeah, here, here, and here. Cool, cool. Part C. The function h is defined by h of x equals blah, blah, blah. Find the x coordinate of each critical point of h, and then classify them. Cool. Well, if you want to find and classify critical points, you got to look for places where... So critical points are places where the derivative is 0 or undefined, right? And then to classify them, you do a sign analysis of the derivative. So critical points of h are places where h prime is 0 or undefined. Well, what is h prime? H prime of x is going to be, well, you just take the derivative. That would be g prime of x minus derivative of this guy here. That's just minus x. Okay. So critical points of h are places where this expression is 0 or undefined. Is this expression undefined anywhere? I mean, certainly this thing presents no problems, like the minus x. Is g prime undefined anywhere? No, it's defined everywhere. You might be tricked into thinking, oh, there are these corners. Yeah, if there are corners in this graph, that means the derivative of this graph is undefined at those locations. Like g, but that would be g double prime. You see what I'm saying? G double prime is definitely undefined here and here and here because those are all corners. But I don't care about that. Like, I'm asking, where is h prime undefined? And h prime only involves g prime, not g double prime. So anyway, so this thing's defined everywhere. I just have to ask, when is it equal to 0? Well, this guy being equal to 0 is the same thing as, oh, mamma mia, g prime of x being equal to x. And what does that mean? Well, yeah, that's kind of tricky to say. I think the best way to think of it is geometrically. That's like asking, when does this graph get crossed by the diagonal line y equals x? You see what I'm saying? Like, you know, here's the diagonal line y equals x, right? Like, okay, that was maybe not perfect, but I think you can see what I'm getting at there. When does that line cross the graph of g prime? I didn't draw it perfectly, but I think you can see that that's going to occur at 3 locations at x equals 0. That's one place. Second place is whatever, like, the coordinates of this point are, which is not super obvious. I think that you sort of have to think about trig, essentially. Because, like, if this, let's put it this way. If this circle were a unit circle, like if it were a radius 1 circle, then the coordinates of this point would be root 2 over 2 comma root 2 over 2, right? It's like the point on the unit circle associated with pi over 4 or 45 degrees. But the radius of this circle is actually 2. So the coordinates of this point are scaled up by a factor of 2. So the x coordinate of this point here is not root 2 over 2. I think it's just root 2. Oh boy. That's a little crazy. I'm kind of wondering if I'm overthinking this. Did I do something stupid? Well, who knows. You guys can see the answers. I'm not going to look. I'm just going to go with it. It's probably going to be fine. And then this point here, 3 comma 3. Yeah, that's obviously supposed to be on this line, right? So these are the 3 critical points of H. Okay. And now to analyze these critical points and figure out whether they're mins, maxes, or neither, you need to do a sign analysis of the derivative. So I got 0, I got root 2, which is like 1 point something, and I got 3. So I got these 3 regions to analyze. Okay, and again, this is a sign analysis for h prime of x. So in this first region here, to the left of 0, I guess I could use a test point. Like, look at -1. Well, actually, it's kind of easy. Look, very easy to tell what the sign is. H prime is just g prime minus x. G prime is this graph here, and x is the diagonal line. So like, is G prime of x minus x positive or negative at -1? Well, at -1, G prime is above x. You see what I mean? Like the graph of G prime is above the diagonal line. So that difference has to be positive. So plus, and then between 0 and root 2, well, you know, root 2 is right here. Wait a second. Why did I, no, back up. Why did I say that x equals 0 is a critical point? That doesn't make any sense. That doesn't make any sense at all. You guys should have stopped me. No, that's, what am I talking about? Like, why did I say, no, the diagonal line does not cross the graph at x equals 0. Stupid. Stupid, stupid, stupid. Okay, so I think, so sorry about that. I don't know why I was thinking that. Yeah, there are just two critical points, right? There are just two critical points. Well, anyway, to the left of root 2, to the left of this point, G prime's bigger than x, so this difference is positive on that region. And then root 2 to 3, the diagonal line is above the graph, so that difference is going to be negative, and then after that, the diagonal line is still above the graph, so it's negative again, right? You see how the diagonal line is above the graph? This is a hard problem. So anyway, what kind of points are these? Well, h is increasing, and then decreasing, and then still decreasing. So root 2 is a local max, and 3 is neither a min nor a max. Oof, okay, moving on. Moving on. Sorry about that weird mix-up where I was, for some reason, thinking that 0 is on the... Anyway. Final question. Rocket A has positive velocity v of t after being launched upward from an initial height of 0 feet at time t equals 0 seconds. The velocity of the rocket is recorded for selected values of t. Okay, so this is velocity. Find the average acceleration of rocket A over the time interval 0 to 80 seconds. Indicate units of measure. Well, so average acceleration. Well, acceleration is the rate of change of velocity. So average acceleration is just the average rate of change of velocity. So average acceleration over the interval 0 to 80 is just going to be the average rate of change of velocity over 0 to 80, which would just be v of 80 minus v of 0 over 80 minus 0. We can get v of 80 and v of 0 from the table. That would be 49 minus 5 over 80. So that's 44 over 80, which is whatever it is. Who cares? And the units of measurement would be, well, what's velocity in? Oh, feet per second. So acceleration must be feet per second squared. B. Using correct units, explain the meaning of this integral in terms of the rocket's flight. And then use a midpoint Riemann sum with 3 subintervals of equal length to approximate that integral. Well, when you integrate velocity, you get displacement. So this is the displacement of the rocket from time 10 to time 70. And the units would be in feet. As far as the approximation of this integral, okay, well, if we're doing a Riemann sum with 3 subintervals of equal length, well, we're dividing the interval from 10 to 70 into 3 equal parts. The total difference is 60, cut that in 3. I think each subinterval is going to be 20 units long. Like, so 10 to 30, 30 to 50, and then 50 to 70. I think those are your three subintervals. We're doing a midpoint Riemann sum. So we're going to use the midpoint to tell us how tall each rectangle is. All right, so let's think about this first rectangle going from 10 to 30. The width, of course, is 20. How tall is it? Well, it's the value of the function at the midpoint. The midpoint is 20. So what is the value at 20? It's 22. Second subinterval, the width is also 20. How tall is the rectangle? It's the value at the midpoint, so it's the value at 40. So that'd be 35 plus, and then 20 times value at 60. That'd be 44. So whatever number this is, that's what it is. Part C. Rocket B, a different rocket, okay. A different rocket is launched upward with an acceleration of blah, 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 feet per second. That's another way of saying feet per second squared. At time t equals 0, the initial height of the rocket is 0 and the initial velocity is 2. Which of the two rockets is traveling faster at time t equals 80 seconds? Explain your answer. So I'm going to find the velocity of rocket B at 80 seconds. That's my goal. All right, so I know the acceleration of rocket B. So the velocity will be, I'm a little wary of calling this v of t. Like we already have a v of t, and it refers to the velocity of rocket A. Maybe just for emphasis, I'll write v subscript b to emphasize I'm talking about the velocity of rocket B. So velocity of rocket B is going to be the antiderivative of, oh god, of 3 over square root of t plus 1 dt. What is the antiderivative of that? I'd rewrite this as 3 times t plus 1 to the negative 1/2 dt. Then you can kind of think about what it should be. I think it's going to be like something t plus 1 to the positive 1/2. That's going to be the exponent. And I think the coefficient in front should be a 6. All right, just double check this. If I take the derivative, do I get what I'm supposed to? Yeah. Technically, this is actually a composition. Like if you take the derivative, you have to do the chain rule. But the inside function is t plus 1, and the derivative of that is just 1. So like this is the correct antiderivative. Take the derivative and you'll see you do get this, right? 1/2 comes down, subtract 1, and then multiplied by the derivative of the inside, but that's just 1. So anyway, so that plus c. Cool. Problem is I need to know what c is, right? I can figure out what c is by using, they give you some kind of information here. They say at time t equals 0, the initial velocity is 2 feet per second. Okay, so 2 feet per second. That means that VB of 0 has to be equal to 2. So that means if I plug 0 in for t into this guy, I should get 2. So 6 times 0 plus 1 to the 1/2. Nope, not what I meant. Plus c should be equal to 2. 0 plus 1 to the 1/2, that's just 1. So that whole first term is just 6. So 6 plus c equals 2. So I think that c is going to be negative 4. So therefore, the velocity function for rocket B is that guy right there. And therefore, the velocity at time 80 is going to be, oh, look at that. They made it so it's a perfect square. How sweet. So that's 6 times 81 to the 1/2 minus 4. If this were the AP, you could just leave this. Like, you don't even have to evaluate anything. But I will. I'm feeling generous. 6 times square root of 81 is 9 minus 4. So 6 times 9 is, oh my god, I'm totally drawing a blank. What is 6 times 9? Well, 6 times 10 is 60, 54. So it's 54. Okay, so that's 50, I think. Cool. That's why, see, that's why on the AP, you shouldn't actually evaluate your arithmetic expressions, because, like, you're just wasting time, and you could make an arithmetic mistake. You could forget what 6 times 9 is. You never know, but you don't have to. Anyway, I think that's it, right? Cool. All right. Hope it was useful, guys. See you later.